So if we look at the rate of a chemical reaction, what does the rate mean? It's a measure of how fast the reaction is making products, or you could think of it as how fast is it using reactants. So we have this graphic here. Here's the clock. Here's my pointer. Oops. Technical issues. Come on, where's my pointer? Hello? It's pointing on both of my screens and not pointing on that screen. There we go. Okay. I did point a couple times earlier, but okay, we'll figure this out. So here's time 0, and here's a reaction with a fast rate. And so we have these blue things called A and these red things called B, and they're going to react and form this green oblong thing labeled C. So at the beginning, all we have is reactants. And as time goes on, come on, pointer. So now we've got a little bit of green and more green, and here at just over 45 seconds, all of the reactants have reacted to produce products. So the reaction is finished. It's done. That's a fast reaction. In the same amount of time, this similar reaction, the colors are different, but it looks very similar, but this is a slow reaction. And so at 15, 16 seconds, we only have one molecule of product made. And at a little after 30, we've got 2, and here we've got 3. This isn't done yet. This was a fast reaction. This is a slow reaction. Okay, so the rate is how fast does the reaction proceed. Well, we use the concept of rate in many other situations and in everyday life, but rate is basically how much a quantity changes in a given period of time. So it's something changing related to time. So the speed of your car, right? How fast is your car traveling? It's the distance that you travel, we usually measure that in miles, divided by an amount of time. So speeds are usually given in miles per hour. So if you drove 65 miles and it took you 1 hour, your speed is 65 miles per hour. What if you drove 30 miles in half an hour? It would be 60 miles per hour, because you take 30 miles divided by half an hour, you're going to get 60 miles per hour. So we can write out an equation. It says speed is the change in distance divided by the change in time. Okay, when we use words like that, it gets kind of long and complicated, and so we revert to using math symbols. Delta, this triangle, lowercase Greek delta. No, uppercase, sorry. Yeah, uppercase Greek delta, I was just testing you. Uppercase Greek delta means change in. So the change in x, the distance, divided by the change in time. We measure the rate of a chemical reaction similarly. We're going to look at the change in the amounts of reactants or products divided by the change in time. So let's look at an example. Here we have a reaction that occurs in the gas phase. We've got hydrogen reacting with iodine and forming hydrogen iodide gas. We're going to define the reaction rate as the negative change in concentration of a reactant, because the reactant concentration is decreasing. So let's look at hydrogen here. Come on, pointer. So if we started out, say, with 1 mole of hydrogen and we let some time elapse, is there going to be more hydrogen or less hydrogen after the reaction goes for a while? There'll be less, right? Because it's getting used up. So the change in hydrogen concentration, remember these brackets around a chemical formula mean the molarity, the concentration in moles per liter. So the concentration of hydrogen at temperature 2, the final temperature, minus the hydrogen concentration at temperature 1. I know.
Oh, sorry.
That's okay. It's just, here it comes. Yeah, it's the math. I love math. But generally speaking, delta, okay, that's not the thing I wanted. I haven't used this for 3 weeks, so. Delta is final minus initial.
Is lowercase t time with uppercase t being temperature?
Yes. Lowercase t is time, uppercase t is temperature. And, because we're trying to be concise and use letters like that, then it becomes very important that we all do it the same way. What's extra confusing is if you go into a different field, or sometimes even a different branch of chemistry, they'll use some of the same letters for different things. Right? That's not good. So the delta in front of anything, delta x, is the final x minus the initial x. Delta is always final minus initial. And you should have seen that in Chem 1A. So it's the final amount of hydrogen minus the initial amount. Well, the hydrogen is a reactant. The final amount is going to be smaller than the initial amount, right? Because it's getting used up. So this guy right here, this quantity, ends up being a negative number, right? Because the final is always smaller than the initial. Well, rates conventionally are expressed as positive numbers. And so in order to make this a positive number, we throw this minus sign in front. So it's the final amount minus the initial amount. That's the change in the hydrogen, the reactant concentration, divided by the change in time, which is the final time minus the initial time. The final time is always higher than the initial time, right? Because time only goes forward. It's convenient that way. So this is the rate equation for a reactant. You have to put a negative in there. This is the rate equation for the other reactant. Any chemical reaction has one rate. Whether you're looking at it as one reactant or the other reactant or one of the products, however you end up calculating it, the rate should come out to be the same, and they're always going to be positive. Any questions? So that's defining the rate as looking at the concentration of a reactant. We can also look at the concentration of a product. So the product concentration is going up. So when we look at the change in HI concentration, the final concentration is going to be larger than the initial. So the change in it is going to be a positive number. And so that's why this one is going to be plus. Now, what's different here is there's this factor of 1/2, right? That is there because of this 2. So let's, the 1/2 relates to the stoichiometry of the reaction. And I'm going to get to that in just a minute. Any questions before I go to the next slide? So pictures are good. So here we have a picture of a hydrogen molecule, picture of an iodine molecule, picture of the 2 hydrogen iodide molecules. So when we destroy one of these, how many of, come on, pointer, look, are they even touching or not? Come on. Hello, thank you. You have to talk to these things. Sometimes you have to be stern with them. How many of these guys do we make for every one of those? 2. So the change in the HI concentration is twice as large as the change in the H2 concentration. If we use up one of these, how many of these do we make? 2. So the change in HI is going to be twice that of this, and it's going to be twice as much as this one. But the rate for the overall reaction needs to be the same. So we solve that by dividing by 2. What on earth? I was really liking this this whole new PowerPoint edition here, but I don't like having that bar at the bottom. I'll have to figure that out another time. This guy down here, I don't like that. Anyway, here's the rate for that. Plus 1/2. So we take this coefficient. It's 1 over the coefficient times the change in this divided by the change in time. Here's a graph from your textbook, and it's obliterated the title at the bottom. The bottom down here is time. So the x-axis here is time in seconds or minutes? It's in seconds. Time in seconds. And the x-axis is concentration in units of molarity. And so the red line here is representing the concentration of the product. At time 0, there's no product. As time goes on, the amount of product increases. That hopefully makes sense. And this line, the green line, is representing the concentration of hydrogen. It starts high at 0 when the reaction begins, and then the concentration of that decreases. So this graph was obtained by measuring the concentration of the reactant hydrogen and the product, hydrogen iodide, at different times. And you can graph it, and you get these nice curves. You can get the rate from the graph like this. So what we're doing to find a rate is we're looking at a particular point in time. So up here we're looking at 50 seconds. At 50 seconds, here we have a concentration of HI. Now this is a curve, isn't it? It's not a straight line. But we can approximate the change by using the tangent of that line. So the tangent of the curve is this black line here. And then we can take this black line and determine the slope of this curve just at that one point. And so here on the y-axis, we can measure the change in the concentration by subtracting this concentration, taking this concentration and subtracting this one. So that looks like 1.56 minus 1, so that's a difference of 0.6 moles per liter. And then the change in time. Here at this point, we are at 30 seconds, and then we're going up here to 70 seconds. So the change in time is 40 seconds. And so to find the rate equals the change in the hydrogen iodide concentration divided by the change in time. And what did I forget? The 1/2. 1/2. Squeeze it in there. So 1/2. And the change in concentration is 0.56 molar divided by the change in time of 40 seconds. .56 divided by 40 divided by 2. Now 0.007. I encourage you to have your calculators out and do the calculations along with me because I make mistakes sometimes. I like to pretend that I'm testing you, but really I just make mistakes. And my general advice for calculations is write it all out, show your work like this, punch it through your calculator twice. If you get the same answer both times, you probably did it correctly. If you get 2 different answers, go for best 2 out of 3. It's really easy to just push a button wrong or do something silly. So what are the units on that? Molarity per second. There's nothing that's canceling out there. This unit is moles per liter, molarity, and second, and so there we have 0.007 molarity per second. Or moles per liter second. Yeah. So let's calculate the rate using the hydrogen concentration. So here the change in the hydrogen concentration is negative because it's going down. So it went down by 0.28 moles per liter. over the same change in time here, 40 seconds. You would not have to use the same time change as you did up here. When you do this practically off of a graph, you're going to do like they did up here, or you can draw this line as long as you want. You might as well go to a point where you feel like you can read it easily off the graph. But so calculating the rate down here, the rate is going to equal what? It's the negative change in the hydrogen concentration divided by the change in time. The 1/2 here was because there was a 2 in front of HI. There was a coefficient of 2. We're dealing with the same reaction. The coefficient for, oh yeah, here it is right there. There's a 2. The coefficient for the hydrogen is 1, and so we don't have to mess with that. So then the change, we got negative 0.28 molar divided by 40 seconds. So we have a negative, negative, so that ends up being a positive, and that comes out to be the same thing. Molarity per second. Do we expect those rates to come out the same?
I was just thinking that, yeah.
We do. The rate should be the same no matter how we calculated it. That is the rate at this particular point in time, at 50 seconds. Now, if you calculate the rate over here, it's going to be different because the rate will change. But at a given time, a given point in time, the rate should be the same regardless of which reactant or product you calculated it from. That's why we have a negative here for the reactants, so that it ends up being a positive number. And that's why we use the coefficient here to account for the fact that the hydrogen iodide is made at twice the rate that the hydrogen is destroyed. But we're talking about the rate of the reaction as a whole. Any questions? So this is data in a table form. So here we have the time in seconds, and here we have the hydrogen concentration in moles per liter, and here we have the change. And so what this is doing here, it's not real obvious, but this number is the difference between these two numbers. So we've got the final 0.819 minus 1, and that gives us a negative 0.181. The time change there is 10 minus 0, so 10 seconds. The rate is negative of the change in hydrogen divided by the change in time. And so we end up with a rate of 0.0181. And you can go through for each time interval and calculate the rate. The rate is not staying the same, is it? No. It's decreasing. This is the average rate during this time period of 0 to 10 seconds. The average rate is this. From 70 to 80 seconds, the average rate is 0.0045 moles per liter second. So the rate is decreasing as the reaction progresses. Why do you think that might be? There's less reactant. Do you remember collision theory from Chem 1A? No? We'll talk briefly about collision theory. So collision theory says that in order for two substances to react, they have to collide. They have to run into each other. They have to run into each other with enough energy to break any existing bonds that needed to be broken, basically to get over this activation energy. They have to run into each other in the correct orientation. It's a little bit like two people meeting and falling in love, right? If you meet under the wrong circumstances, it might not happen. But if you met under the correct circumstances, it would happen. So not every collision causes a reaction. The likelihood of having a collision cause a reaction will increase with the number of collisions, right? If you have more collisions, then you're going to get more reaction. You're going to have more collisions when you have more reactant molecules. As the concentration goes down, there's fewer and fewer molecules. They're just not going to collide as frequently. That's why it's a lot easier to meet someone that you're going to click with and maybe fall in love with in a bar, in a crowded place, right? If you go out to the field where there's one cowboy at the other end of the field, are you likely to meet anybody? No, because the concentration of guys is really low, right? Yeah, you might run into that guy. A reaction could still happen, but the rate of the reaction is going to be a lot less. Does that make sense? Okay, so as the reaction proceeds, the concentration of this reactant decreases, and therefore the rate of the reaction goes down. Oops. So the instantaneous rate is what we calculated earlier looking at this graph. The instantaneous rate is the rate at a particular point in time, not the average over a short period of time, but at an individual point of time. And we calculated that using the tangent of this curve. I got ahead of myself. I was supposed to do that calculation here. Oh well. So let's look at this in more generic terms. So we had our one example equation reaction there with the hydrogen and the iodine. Here we're going to use letters if we have A and B reacting to form C and D. And these lowercase letters are representing the coefficients in front of those chemicals. Then we can generalize rate equations. So the rate would be equal to minus 1 over A, because this is the coefficient on A. It's negative, why? Because it's a reactant and the concentration is decreasing, times the change in the concentration of that reactant divided by the change in the concentration of time. We can also say that's equal to minus 1 over B times the change in the concentration of B divided by time. And that's equal to 1 over C times the concentration of C. This one's positive because that concentration is increasing. And this one is also positive. So if we know the rate of change for one of the species, one of the reactants or products, we can figure out the rate of change of any other species during that same time. But only at that time. We cannot use this to predict what's going to happen in 5 minutes, because this is an instantaneous rate, and as we saw, it was changing as the concentrations changed. Any questions? So let's do some examples. There are examples within the chapter in your textbook. And I know from experience that a lot of students don't look at them. And so to make it easy on myself, I'm using some of those as my examples during lecture. Some of them, like this one, is the actual example. This one is worked out in your text. And then there are also for practice ones that I will almost always do in class. Those are not worked out. But so here's an example expressing reaction rate. So it says, consider this balanced chemical equation. It says, in the first 10 seconds, the concentration of iodide ion drops from 1 molar to 0.868 molar. Calculate the average rate of this reaction in that time interval. So we have information about the iodide concentration. So then we're going to say the rate equals something to do with the iodide concentration, because we don't know about any of the other species. So the rate equals so here's iodide. That's a reactant, so this needs to be negative. Is there a coefficient in front of it? 3. So we're going to multiply this by 1 over 3. 1 over the coefficient, and then we're going to do delta I minus divided by delta T. So the change in the concentration of that reactant divided by the change in time. So what is the change in reactant concentration? We'll take the final, the last one, 0.868. And the initial was 1, so minus 1.00. Negative 0.132. That sounds good. Do we have any arguments about that? You okay with that? So that's the change. We took the final minus the initial, and now we can plug this in. So it's minus 1/3 times negative 0.132 molar. And what's the change in time? 10 seconds. It says in the first 10 seconds. So that's from 0 to 10 seconds. So that's just, they gave us the change. I highly encourage you to learn how to show your work if you have not already done that. This is showing your work. This is writing the equation, then writing the equation again with the values plugged into it. Then you do the calculation and write down the answer. It's a little tedious sometimes, but ultimately it does save you time because you get the correct answer more often. And try to be neat. Because one of the things about being a scientist is you have to be able to communicate with other people, and that includes future you, right? You should be able to look back at this in 3 years and be able to figure out what it was you were scribbling about. So I'm doing this on my calculator, and I'm coming up with 0.0044, and that's going to be molarity per second. What about sig figs? Sig figs are not going to go away. There should be 3. Because this number, remember, leading zeros don't count. This has 3. This has 3 because that's a trailing 0 with a decimal point. This is an exact number. And how many does this one have?
4.
Leading zeros are not significant. So this one only has 2. So we need to add a 0 at the end. So 0.00440 molarity per second.
Now, what would the given numbers for us? Are we supposed to take those into consideration? Like 0.868.
Yeah, 0.868. We're going to assume that the person who wrote this was aware of significant figures and wrote that, meaning that there was uncertainty in this 8 at the end. So this one has 3 sig figs. This one has 4. But when we subtracted here, the rule for subtraction is we keep the same number of decimal places. And so this came out correct, even though we didn't pay attention to it. So if you're rusty on your sig figs, go back and look at that section in the book. And feel free to ask questions, but we're just going to continue using significant figures. So any questions about that one? So part B is determine the rate of change in the concentration of H plus during that time interval. So this is dependent on the information from part A. So in part A, we found that the rate was equal to 0.00440 molarity per second. That was the rate of change of the iodide. Well, that's the rate of the reaction. So in terms, what they're asking us to find here is delta H plus over delta T. Okay, so this is not something we explicitly have done yet. What have we done? We could find the rate in terms of H plus, right? We learned how to do that. So let's write that equation down. Sometimes when you're doing problems like this, you don't know exactly how to proceed all the way through, and you just have to kind of write down some ideas and put them together like a jigsaw puzzle. So we could say the rate in terms of hydrogen is what? Is it minus or plus? Here we've got H plus. Is it a reactant or a product?
That is.
It's a reactant, so then the rate is going to equal negative 1 over the coefficient. What's the coefficient? 2. So negative 1/2 times delta, H plus over delta T. Okay. Is this rate going to be numerically equal to that rate?
Should be.
Yeah, they're going to be the same. That's the rate of the reaction. Yeah, at that particular time, over that interval. And so this is equal to 0.00440 molarity per second. Oh, this is what they're looking for. Let's see. So this is what I want to end up with. Now, can we see how we would find that? We need to get this minus 1/2 to the other side, right? So then we're going to multiply by the opposite, basically. So we've got a minus here. If we multiply both sides by -1, that's going to become positive, right? So we'll multiply by -1. And you have to do the same thing to both sides, because like a teeter-totter, and you want it to stay balanced. And how can I get rid of 1 divided by 2? Multiply by 2. So I'll multiply this side by 2, and the 2's cancel out, and the minuses canceled out. I also have to multiply the other side by 2. So then I end up with negative 0.00880 molarity per second. So the concentration of hydrogen is decreasing at a rate that is different than the overall reaction. The overall reaction rate is 0.00440. The rate of change of the hydrogen ion concentration is greater than that. Any questions?
If it were just hydrogen and not a hydrogen ion, would we have to account for the hydrogen in the H2O2 as well?
No. Whatever we're looking at in here is going to be one of these reactants or products. So in this one, because it doesn't have just H, a hydrogen atom, as a reactant or a product, we would not look at that.
Okay.
Good question. Any other questions? Yes?
So the time interval was 1 second?
The time interval was 10 seconds.
So why didn't you multiply by negative 10? Shouldn't it be negative 10?
This is the equation for the rate as a function of hydrogen ion concentration. So minus 1 over the coefficient times the change in that divided by the change in time. I know what I should do to be a little more clear here. This is not the rate.
Oh, yeah.
This is delta H plus over delta T. Does that help? Yeah, that's because what I've solved for is what's in this box. This is the change in hydrogen ion concentration per change in time. So it's going to go down 0.00880 moles per liter in every second, on average, in that time period. It's per second. In 10 seconds, it would be 0.088. We're going to be doing a lot more with rates and ideas like this. And so the time to see it, to understand it, is right now. If it's not making sense now, this is the time to ask the question. I love questions. Okay, so this is the next example. This is for practice, also expressing reaction rates. So the previous 2 slides are actually worked out in your textbook. This one's not. They just give you the question. So that same reaction, predict the rate of change in concentration of hydrogen peroxide, H2O2, and I3 minus during that same time interval. this is very similar to the question we just answered in Part B. That's why I couldn't just do this one without doing the first two. So from the first part, from Part A, we learned that the rate was equal to 0.00440 molarity per second. Now they're asking for the change in H2O2. That's this part. Well, let's think about what we know. We know how to write a rate equation for that, right? The rate will equal, what will it be in terms of H2O2? Negative.
That's it.
Negative delta H2O2, because the coefficient there is 1, right? And 1 over 1 is 1, and we can ignore him. Chemists don't like the number 1. So the rate of the reaction is the same, regardless of what we're looking at. So this is equal to 0.00440 molarity per second. What we're trying to find, though, is this. How is that different from this? It's just a change in sign, right? So we need to lose the negative sign. So we're going to solve for this. And so when we solve for that, we get delta H2O2 divided by delta T equals negative 0.00440 molarity per second. What's the rate for the I3 minus? It's got delta I3 minus over delta T in there somewhere. What do we need to throw in the front of that? It's just positive, right? So maybe we'll just put a plus in there so that we know that we considered. I3 minus is a product. Its concentration is increasing, and so the rate equation doesn't need a negative. And the coefficient here is 1. And so this is just equal to that. So the H2O2 is decreasing at a rate of 0.0040 molarity per second. The I3 minus is increasing at a rate of 0.00440 molarity per second. Any questions? Well, how do we measure the reaction rate? How do you measure the speed of a car? Miles per hour is the units, but how will you actually determine that? You actually measure the distance that was traveled and you measure the time, right? So when we're measuring a reaction rate, we need to be able to measure the concentration of at least one component. Yes?
How do you measure it?
Well, we'll get to that. It's a good question. So we just learned that if we know the rate of change of one, we can calculate the others. We can get the rate of the reaction from any of them. It doesn't matter which one. So we just need one of the components. We need to be able to measure that concentration as a function of time. There's two basic approaches to this. For a fast reaction, perhaps something that's going to be finished in less than an hour, that would be considered a fast reaction. It's probably best to use continuous monitoring of the concentration. We're just going to measure the concentration continuously. For something that happens more slowly, we can sample it at various times. And so, you start the reaction and you know what the initial concentration was. And maybe 2 hours later, you're going to pull a sample out and measure the concentration. And then after 4 hours, you'll do the same thing. And so you'll get specific points in time. So for the continuous monitoring, your book talks about 3 techniques in which you could do that. There are more, but these are just perhaps the most common. Polarimetry. It turns out that some chemical substances, like sugars, will rotate polarized light. And so you can use a polarimeter and you can actually measure how much they're rotating the light, and that is related to the concentration of the sugar. So by looking at the rotation of the light, you can measure the concentration. And that's something that you can do on a continuous basis. Another method is total pressure. If you have gases in a mixture, the total pressure of that gas is going to be related stoichiometrically to the quantities of the individual gases. So here's an example. If you have two N2O molecules, they're going to decompose into 2 nitrogen molecules and 1 oxygen molecule. We learned from Dalton's law of partial pressures that the pressure of a mixture of gases depends on the number of moles of gas, not on what they are. How many moles are on the reactant side?
2,
And how many moles are on the product side?
3.
3. 2 moles of nitrogen and 1 mole of oxygen. So as the reaction goes on, is the pressure in the container going to go up or down? It's going to go up, because as the reaction proceeds, we form more molecules. So the pressure goes up. So there's some math involved in doing the calculations, but the pressure is a measure of concentration. Another technique is spectroscopy. We touched on spectroscopy in 1A. We talked about wavelengths of light and how light is absorbed and emitted by different elements. So spectroscopy measures the amount of light of a particular wavelength that is absorbed by one of the components. So here's an illustration of how that works out. Simple diagram of a spectrometer. So you've got some sort of a light source, and the light is passed through a slit. The slit is passed through a prism, a monochromator, and that separates the light into its different wavelengths. Then we can select one wavelength to pass through our sample. The sample will absorb some of that light, and the detector is going to let us know how much was absorbed. And the detector will be connected to a computer, which will give us a readout of what the absorbance is. And an example is this hydrogen and iodine reaction. What color is hydrogen gas? Not what does it emit if you excite it, but just like if you had a tube of hydrogen gas, does it have a color? No, it doesn't. So hydrogen gas is colorless. Does anybody know what color iodine gas is? Purple. They usually call it violet. Sounds fancier. It's purple. So that's violet. Hydrogen iodide is also colorless. So why is iodine purple in color? It's interacting with light. White light shining on iodine gas, it's reflecting the purple light and it's absorbing the other colors. So usually what we'll do here is we'll select the complementary color to the violet and we'll measure the absorbance of that, because that's what this iodine is absorbing. So we've got our initial reaction, we've got some hydrogen and some iodine, and as the reaction proceeds, these guys go away and this is formed. What's going to happen to the intensity of the purple color? It's going to go down and down and down, and if the reaction goes to completion, it will not be purple at the end at all. So the measure of the absorbance will go down, and that is related to the concentration of that colored compound. And so that is a way that you can continuously monitor the concentration, because this is a technique that is very fast. Light travels very quickly, right, at the speed of light, and so you can send little pulses through here, and your computer's fast, and so you can get a continuous readout as the concentration changes. For slower reactions, yeah, question?
I have a question about the total pressure.
Okay.
Method. To measure the total pressure, you have to have it in a closed system.
Mm-hmm.
So doing that, in this case, the pressure would increase.
Mm-hmm.
But if the pressure increases, that means more of them are in solution, and wouldn't that in turn change the rate of reaction?
having it in a pressurized situation, the increasing pressure could affect the rate of the reaction. Yes. And so it's not, I would not consider that to be a straightforward thing. Because if you remember Le Chatelier's principle in equilibrium, we can affect, if this was an equilibrium, we can affect the position of the equilibrium by putting pressure on it and causing it to shift one way or the other. So one way around that might be to change the volume of the container to keep the pressure constant. And so that's a related aspect to looking at total pressure. Yeah, it's all related. Good question. So for periodic sampling, what we do is we have this reaction going on, and we're going to take aliquots, that's the fancy word for samples. We're going to take an aliquot, a sample, out of the reaction mixture and measure the concentration of one of the reactants or products. And we'll measure the time that we took it out so that we can get a point to make a graph out of. And so we're going to use some sort of a quantitative analysis technique to measure the concentration. There's lots of different things that could be done. You could do a titration. If one of the components was an acid or base, bless you, you could potentially titrate it and see how much is there. Why would you not want to use something like titration as an analysis method on a reaction that proceeded very quickly? The titration might take a while. And when you take that aliquot out, does it stop reacting? No, it doesn't. The reaction is continuing on. So if you have a very slow reaction, the amount of time it takes you to take that out and titrate it isn't going to be a big deal. If you have a reaction that's over in 5 minutes, that's not going to work. That's why we use continuous sampling for those fast reactions. Another thing you can do is gravimetric analysis. Do you remember the barium sulfate lab? With the little crucibles and ashing, and yeah, that was, your experience with that might have varied, but my students probably don't remember that one with fondness. It took 2 whole weeks. Yeah, so it's not exactly a fast technique. The initial part of it, though, would be go very quickly. So if you were measuring, for example, sulfate was one of the reactants or products that you were measuring. You pull the aliquot out, you add barium chloride to precipitate the sulfate. Now you've got all the sulfate out. Now you can take your sweet time separating that. But gravimetric means you're separating it out and then you're weighing it to find out how much of it there was. Another technique is gas chromatography. Gas chromatography is awesome because you can measure concentrations of various components of a mixture. So you have a reaction mixture here. With a gas chromatograph, you might be able to measure the concentrations of both of the reactants and both of the products. So let's look real quick at how this goes. So what we've got here is this injection port where you can put your aliquot in. We have a carrier gas. A gas is going through this column, and this column has some sort of a coating on it. And when we inject our sample in here, the sample is going to be carried along by this gas. Now, the components of the mixture are going to be separated based on differences in physical and chemical properties. So chromatography, if you remember the paper chromatography that you probably did where we put dots of ink and then we stuck it in a solvent, and as it traveled up the paper, the different colors separated. Because you have a mobile phase, here it's the gas, and you have a stationary phase. Here it's the inside of this column. On paper chromatography, it's the actual paper. Well, some of the components are more attracted to the mobile phase, the gas, and some are more attracted to the column, the stationary phase. And so they're going to separate out. And they'll come out over here, and then we need some sort of a detector so that we can see when they're coming out. And you'll end up with something like this as your result. You'll get these peaks. And each peak represents one of the components of the mixture coming out of the detector. They're going to come out at different times. We can measure the concentration by finding the area under the peak. And so we can measure the concentration of several components that way. But this, again, is a sampling at a distinct period in time. You take a sample, you stick it in here, and you find the concentrations.